Hello everyone, welcome to the Exploring Machine Intelligence class, a class where we study about deep learning for artists. And today's class will be about generative models. So the motivation for today will be to understand this glyph and use some model to convert latent vectors into some image representations. And what that means we will see in today's class. So what we saw in the previous class, the previous one we took together, is our models which were about classification. So we talked about the AlexNet model, which is able of describing an image which is on the input as a sort of higher dimensional vector representation here or directly classified. And so this is the task of classification. What we would like to do is sort of flip this task, and by that I mean basically be able to tell it, oh hey, I want this one particular class, and see what the model is able to synthesize as it generate as an image, as an sample of that class. Well, it turns out that this task is much more difficult than the previous one. I guess you are compressing information here, whereas here you are actually creating the information. And so there is a lot of information you don't have when you are going up this model. And so there are various tricks how to do this, and we will basically talk about them over today's class. So instead of these diagrams, we will usually show these representations of the models. Keep in mind that there are a combination of the convolutional layers, which we studied about last class, and then also some fully connected layers and some additional tricks, but the main body of the network is basically built from these two. Oh, right, and also the downscaling layers, which are then turned into upscaling layers here, as we will see. Okay, so today's topic will be going through several generative models and talking about two particular architectures. One of them will be the AutoEncoders, and the second one will be the Generative Adversarial Networks. And in both cases, we will show how they work. We will explore how we can interact with these models, and we will show some examples of artists working and misusing these models as well, some weird uses. Okay, and in the later section, we will get into in the practical session, we will get into using one of these models and also maybe talk about scraping of the internet to collect our own datasets. Okay. So far, what we worked with was mostly classification models. So you had a image and you wanted to have a classification, or maybe get a feature description, etc. And so these are sort of models which are used in analysis. You are compressing the large information which is contained in the image into some descriptor feature that is sort of compressed and has the important information in it. So today we will talk about the other task, sort of trying to create new images or new imagery, which corresponds to some training dataset. So basically mimic the image or like the shapes and the images and the data that is somewhere in the dataset with our own models. And this is a task called or generation. Okay, and so with this comes in mind the question if all of this is actually creative, if when we are generating something, if on its own the machine that is generating these is actually creative. So remember a little bit the creative adversarial GANs that we read about or skimmed through in the first class, or as a homework from the first class. We will sort of keep that in mind, and then during today's class we'll sort of try to ask questions, sort of like where in these descriptions of technology you can actually use some where you can have some control over these models. So where you can sort of exercise some sort of artistic input over these. Okay, so this is a schematic of a generative model where we go from a latent representation, so this is a vector, into an image representation. So this could be 512 numbers, and this could be 1000 by 1000 RGB image. And so what happens here is that we are generating that image. Okay, we will meet this schema again and again, but right now let's see one of these possible architectures, and that is the AutoEncoder model. So as I briefly was saying at the start of the class, even though if we have labels here and if we have images here, this task on its own is too difficult to sort of to map for the model to train. So basically it doesn't have enough data to fill in all the blanks in there. So we are trying to maybe use a few tricks, and one of those tricks is to rephrase this generative task with this identity operation. So you come with an image, you want the network here to represent that image as a vector, and then what you want from the network is to recreate this image here. So what we are mapping from here to here is basically a identity operation. So almost nothing happens. Well, we want for nothing to happen. We want this image to be recreated perfectly. What this model has to kind of figure out on its own is how we can go from that image representation through the bottleneck here, through this latent vector representation, a sort of compressed representation, if you will, and then how to turn that back and then go back into the original image. And so seemingly this is a useless task because we are sort of making a machine for nothing. Go from an image and then don't change anything on it. But as we saw in the previous classes, we were talking about using just parts of the networks as well, right? So when we were having a AlexNet network, a part of that network could be used as a feature extractor. And so in this case as well, we will sort of call different parts of this model as different with different names and assign them different sort of functionalities. So there is a part of the model which is called encoder, and then a part of the model which is called the decoder. The encoder is responsible for encoding this image, this 1000 by 1000 pixels, into a latent vector, which is 512 numbers, let's say, and then the decoder has the same task, but other way around. So going from that latent vector, from this vector representation, back into the image domain. Okay, so we will see in more detail how this, what exactly happens there, but yeah. So what happens here is that this is the AutoEncoder model. It is basically it's the same thing that was shown here. There is an encoder part, some sort of latent representation, and then decoder. And if we look at this, this is a visualization of the layers inside this model. So what you can see here are layers of types of convolutional layers, pooling layers, so the downscaling layers, some fully connected layers, so everything connected with everything, sort of, and then some unpooling or scaling up layers, so which are something which is sort of an inverse operation to the pooling, to the downsampling layer. So if you look at this top part of this network, we have an image, we have a bunch of convolutions which are repeated. So these are 2 layers of convolutions with a resolution of 24 by 24. I mean, they lost some information at the edges here, but it's basically the same resolution as the input. Then there is a pooling layer, which means that it's downsampled by 2. Then again, a convolution, pooling. So this at this moment we have 4 by 4 pixels. And then what happens is that we have a fully connected or flattening and then fully connected layers. So the image has been flattened into single vector, and that is displayed here. There's 250 numbers in this vector, and basically it's wild in the sense that there are lots of values there. We don't really know what's there anymore because we have sort of lost this locality that we had when we used just convolutional layers. Well, so this first fully connected layer is connected with another, with another, with another, with another, and sort of here we have a vector which is the sort of a bottleneck. So here we have 10 numbers which are representing this image as a sort of classification, if you will. So you can imagine that this top part is basically the same as a network which has been trained to identify these numbers. Instead of the labels of saying 5 and firing up on the 5 category, we just leave it sort of at whatever the model wants for this latent representation to be. Well, so we can relate this top part to a classification network, and this is the encoder. And from there, we want to sort of recreate this image back. Well, how to do that is sort of to go one by one and then sort of undo the effect that there is in these layers, right? So there is a two fully connected layers here, and then we have a we sort of rescale this into the original dimensions. So 4x4 by 36, again 4x4 pixel images, and we have 36 channels of different convolutions. Well, there is noise still here, and we sort of cannot really recognize anything. But we then add convolutions after these, and then scale them up using unpooling, and then again convolution, then again convolution, then again pooling, sort of scaling up all the way till until we get to a 28 by 28 resolution, and then at the end finally sort of convert this into a normalized representation. And sort of this representation should be similar or ideally the same as the one we had here. Well, there was a lot of detail here. I think it's not really that important to know all of these layers, right? But it's important to understand the concept that we are going from a real image here back to that same real image. And through that job, we are going through a bunch of layers, and one of those layers is a single vector layer which has 10 numbers in this case, and that layer is the one which is called the latent vector, or the latent vector representation. And what it means is that we are sort of pushing in this image through this compression, and then we force it to compress into these 10 numbers, and then force it to sort of decompress from those 10 numbers. So if you look back, we are sort of forcing this image to be compressed into these 10 numbers and back into the original image. Okay? So how would we go about training a model like this? Well, so let's see this this illustration. It's we have an image here. We are encoding it into the vector, which we can call Z, and then we are decoding that vector into an image which should be the same as this one. Well, so the training is we will be somehow comparing these two images, the image I at the start and then the reconstructed image. And as we were saying, we sort of want the reconstruction to be perfect. So we want these two to sort of equal or be very close to each other. Well, so how do we sort of mathematically describe this image here? Well, if you feed this original image through this network, so this I, if it goes through E, like this, you will get a vector, Z representation vector. And then if you feed that vector, so feed this Z through the discriminator again, or the decoder, sorry, jumping ahead. If you feed that through the decoder again, you are going to receive the same image here. And so we can call this the reconstructed image as this operation. And so what we care about is to have some sort of distance metric between this reconstructed image and this original image. And so you're basically comparing pixel by pixel these two images. And so, for example, the what is used is the mean square error here, and that's basically a distance between each pixels, which is squared and then summed over the whole image. Okay, well, there are some variations to this single sort of architecture. There are infinity of types of autoencoders and different implementations, but a huge different type of these is the so-called variational autoencoder. And if you look at this representation, it is mostly the same. What we have there is that, as an addition, is that we are sort of trying to impose some additional rules about this latent vector. So where here we are sort of allowing it to have whatever it wants in there, however large numbers sort of, we will allow it just to train end to end. In here, in the variational autoencoders side, we are sort of trying to maintain some or impose some additional rules. So one of them is, for example, that this latent vector has to have should have the Gaussian distribution. And so there are also some other sort of terminology from probability theory, which is sort of describing how this model works. And so it's a bit too complicated for us now. I think we don't have to also jump into the details. The overall working of this network is the same as this one, basically. If you are interested in that, you can see this block, which is describing it quite nicely. Also the basic autoencoder versions and also the variational autoencoders, and then some other beta variational autoencoders, some other types of some specific types of implementations of variational autoencoders. Okay, so we have made it. Basically, we have trained an autoencoder model. We forced this network to work somehow. With the trading scheme shown in the previous slide, where we are forcing an image to be encoded and then decoding that image into the original reconstruction of that image. And now we sort of want to see how we can interact with this model. Because if we ended here, if we ended with a model which is sort of just representing an image and then reconstructing it back, it would be boring, really. So what we want to do is to sort of generate new images. And basically that happens by throwing away this part of the network and just focusing on the decoder segment. And so we can almost consider this decoder as a generator from now on, because we are throwing some latent vectors in here. So we are just throwing some random numbers here, and we are getting some images which are sort of corresponding to the data set that this model was trained on. Okay, well, so what happens is that with some random vector z1, we will get a random image. So we will throw in a random vector. Let's say this is 512 real numbers. The vector will be something like this. This is randomly chosen. And the decoder produces an image which will be, let's say, something like this. So this is basic sort of operations with these models. If we throw different random vectors in here, so let's say z2, which is the same dimensionality and everything, we will have another sort of image. Well, and so here is the moment where this starts to be more interesting, because these are simple vectors, and these 512 numbers are something, or these two vectors are something that we can sort of mix. So we can, for example, explore what would be the sort of 40% of this vector plus 40% or 60% of this vector, and then they add up to 1. So this is a linear combination of these two vectors. So they will also create a vector, let's say z3, which is of the same dimensionality and roughly the same sort of distribution, because we are combining them sort of not adding too large amount of any one of them, right? So, and this mixture is something that we can sort of move around, right? And so what happens is that if we throw this mixed vector here, we will use this decoder. It will create an image. Of course it will. Any vector that we throw in will create an image. But the properties of this image will be that this image is also a sort of mixture of these two original samples. So if you look at this whole spectrum, we can sort of make an interpolation through this space. Well, and how to make the interpolation? We are sort of just going with a which is going from 0 to 1. So basically going from Z1 all the way to Z2, and sort of sampling at different moments, and then creating images which are sort of on the road between these two real samples. And so this goes. This is something which is really interesting, because if we were to sort of just naively mix images, which is consider this is a matrix of like 28 by 28 pixels, and if you are just mixing them, like if you take half of this image and half of this image, you will get a messy thing like here, which is something like, yeah, both of the numbers there are visible, right? Because you're just taking pixel by pixel all of those values and mixing them together. So you will have grays here, and then also grays here, and then some number here. This is actually a mixture of those two images, but it's not something that we would sort of understand conceptually. This is not a mixture of these two numbers. Conceptually, it's a mixture in a sort of pixel space. And so if we instead had a model which was trained on these numbers, which sort of captured the whole distribution of the dataset in it, and then you are sort of mixing in the latent vectors, what happens is that this model has sort of learned how to generalize over this dataset, and it has learned the way how samples should be in different categories. And so if you explore somewhere in the middle of these two categories, you will be getting some images which are sort of somewhere in the middle. And so you can get sort of interpolations between images in a latent space rather than in the pixel space. And so, whereas this was a sort of messy pixel mixture, this is almost a conceptual mixture of those two concepts which we had here. I guess what is important to say at this moment is that this is a conceptual mixture of those two topics, or of those two samples, but this mixture is done purely in visual sense. So the model itself doesn't have any additional information about what these numbers, that these are even numbers. It doesn't know it per se, but because we have thrown a large dataset of these images, it has learned the sort of visual representations of these, sort of clustered them together in its own sort of memory, and then if we go through this, we are sort of recalling the latent representations of these samples. So what I would like to talk about is one specific type of interaction that we can have with autoencoders. And if you remember, in the autoencoder model, we can encode real samples and get their latent representations. So this is sort of using both parts of the model, not just the discriminate or the decoder part, but also the encoder. So you can take real samples of real people, sort of, and then encode them using a model which was trained on this dataset of faces, let's say. And yeah, like, by the way, these encoded images are quite often not really reconstructed perfectly. So you can see that there was a loss here, right? So this is the encoded image, and this is the direct reconstruction of that image. The same happens here, and the same happened here. And so what you can sort of see is that these faces have lost some details. They are sort of blurred out versions of their own sort of the real images. We will talk about that a little bit later as well. Well, at this moment, you have three latent vectors and their representations. And so what you can do is sort of explore this space and explore interpolations between these previous latent vectors, which are sort of corresponding to something real. So you can sort of mix samples which were real, and then sort of explore what would happen if you are mixing these two ladies and this guy, and you would get some sort of like version of this face. So you can use these to generate interpolations, and you can use these to generate interpolations even as an animation, for example. So going little bit by little bit and then showing that as a frame by frame. The important thing to note here is that we are sort of combining three vectors, Z1, Z2, Z3, which are these three faces, and then that the combination is linear. So we are sort of adding up these to add up to 1, these ABCs. Okay. So another sort of actually really quite cool part about autoencoders and other generative models is that being able to encode images into some latent representation, we can use some tricks like this. So you can imagine this space is a sort of high-dimensional space. So you can imagine it as like a cloth over a table, let's say, but that would work in a 3D. And also this is not a table, right? But this would work in a 3D. But we don't want it to work in 3D, but because we had images or latent vectors which were with the 512 numbers, let's say that this is a 512 dimensional cloth somewhere in space. And this is a space that we can sort of use to compare or to throw the real samples and encode them into that space. So what that means is that we can take a face of this dude and sort of encode that into a single point of this high dimensional space. And you can imagine that each space of this, each point of this high dimensional space corresponds to one sort of point, to one vector of 512 numbers. So this is really difficult to get. I guess it's easy when you imagine this is 3 dimensions and so you're sort of moving in x, y, z in these 3 coordinates, but somewhere behind these there are these other 512 dimensions as well. But it's not really that important. Let's just think about it as 3D in this case. Well, so we are able to encode one sample here, and then let's say encode some other samples here. So these are all faces. And as you can also notice that these are all smiling faces. Well, so if we encode these images, we will see that they are sort of maybe in this space, in this high dimensional space, maybe they are sort of dropping at somewhere near each other, somewhere here. And if we encode other types of images, let's say from this category, from not smiling faces, let's say that they would fall in sort of this part of this high dimensional space. Well, this is a simplification, of course, but like let's say that these are dropping somewhere here. And when I'm saying that these are falling here and these are falling here, what I mean is that there is an autoencoder model which is representing these images as latent vectors, which would be sort of falling into this part, and then these images which would be falling into this part. And the reason why there is even a distinction between these two is that the model itself has to be trained on datasets containing these images. So let's say we have an amazing model which is trained on many faces, and so it can sort of make these distinctions. Well, okay, so if you noticed, these faces are the same. So this is actually coming from some research someone made about detecting smile and fake smile as well, actually. And you can even look at the differences between sort of the samples. Well, I guess as you will know now, we will not compare these in the pixel space, but we can sort of compare them in this high dimensional space and sort of look at this difference. So is there something that we can sort of describe as, hey, this is the difference which corresponds to the smile? Basically, a vector which is, if we add it here, we get the same sample, so the same guy, but smiling. Well, so it turns out if you look at, or if you encode enough images of one type and then enough images of another type, so basically explore one property and then encode enough samples from two types of this property, you can sort of make clusters of where these encodings fell in that high dimensional space. And maybe you can sort of get a centroid or like a center point of these clusters. Well, so this is not just a sphere or something. This is high dimensional subspace of the high dimensional space. So this is maybe something which is easily written here, but maybe it's actually quite difficult. But let's not worry about that. Let's say that we can have these blobs somewhere, hyper blobs in the hyperspace, and then get these points and sort of get a universal vector which is sort of corresponding to this smile operation. And so if you look at these original images or these original representations, if you take this image here and then give it this smile vector, it will move it somewhere around this smiling sample. Well, given the fact that we have an AutoEncoder model, this high dimensional space is an intermediate representation. We can encode images from here to here, but we can also encode images from the hyperdimensional space, from the vector space, back into real images. So we could really take this image, encode it, move it here, and then decode it and sort of get maybe something similar to this guy. Well, this is called latent space arithmetics, because we are sort of doing some math in the latent space, basically. And these individual vectors are sort of called visual attribute vectors. So we have chosen the visual attribute of smile and extracted it from the dataset as one dimension that we can sort of move images on. Well, how does this work at all? Or let's see in this example. So this is a work where it's basically this. It's basically trying to get visual attributes as a vector. And so you encode a real image, Agent Smith, and then you sort of move this image or the encoding of that image across different vectors, across different sort of, in the high dimensional space, you're sort of moving it with these different vectors. So one of them will be the smile vector, and that one will sort of move this guy into these samples. Well, this is a purely visual data set, and this has been trained on some faces, and so I'm not the one who chose these categories, but let's say that there are other categories like eyeglasses vector, like a smile vector, like hair, blonde hair, bangs, like age vector, and also something which is called female vector. Well, so this heavily depends on what we have labeled as smile or as blonde or as female, which is actually not as simple to do, right? It's not something which should be done super easily. You cannot really do that with just simple visual information. And so this is where these models maybe fail, because what we have encoded here is just the visual information and maybe some labels that we assigned to it. This doesn't understand it in conceptual sense as humans would. This simply understands it in the way how images which are similar to each other visually are differentiated. Well, so there are some complications, right? And actually, even this plot is a work of a GAN, but it illustrates this point nicely, because you can do something like this with the AutoEncoder. You would take this image at the start, encode it into the latent representation, plus the smile vector, and then decode that, and you would get these faces. Well, let's see this animation. It's a representation or like a visualization of what we just talked about. So these are some encoded faces, and we are basically moving them in the direction of a smile vector, right? So this guy, or this guy, or I don't know, actually, this person is being moved in the direction of smile, and what it means visually in the dataset is that they get smiling. You can remove smiles as well, so you are moving basically in the other direction of that vector. you can add sunglasses or eyeglasses as a vector, or you can remove them as well. And so this is sort of moving around through the hyperspace of the model. Okay. As a side note, I will say that all of these models have been trained on the celeb A dataset, and that is a dataset containing celebrities. And I think this was created because celebrities have a lot of photos that you can download from the internet for free, and it's not that difficult to collect it. But there is some concerns in there about the diversity of samples. So ideally, you would have a dataset where there is a large diversity of samples, where there are equal numbers of samples in each of these categories, and also where the categories are made sensibly. So where you create this category is sort of where you're separating the hyperspace of the images, or like creating a plane of division between those images. So if you call someone who has eyeglasses and who doesn't have eyeglasses, I guess that's all right. But if you categorize it on some other dimensions, then it becomes slightly more problematic. And you can sort of go endlessly there. I will not dive too deeply into this. There were some attempts to make more diverse dataset. There were some problems with those datasets as well, because they were collecting images from the internet without everyone knowing, sort of. So it's sort of, but these datasets then again are sort of created from 30,000 images. And so how would you collect a dataset like that? Well, so that is quite complicated area, but I still wanted to kind of say or mention this here, because this also sort of explains why we saw the images that we saw before. Okay, well, so we went through the more or less basic uses of autoencoders. We talked about two cool applications that you can use, sort of, with these. So being able to interpolate between samples, and then being able to sort of extract visual attribute vectors and then move your samples through them with them. Let's talk about some weird uses. Well, so the first one is that you sometimes might need a sort of arbitrary feature encoder. So I guess you will appreciate it after the last class that you had with Rebecca Fiebring, and there we had sometimes like we were building some interactive tools, right? So you had maybe images here at the start, and you wanted to plug it into I don't know, some amount of numbers, and then use those numbers to control your tool or application or basically anything. And so it may happen that you need a feature extractor that will describe this image as some, let's say, 10 numbers here. And so if we had these numbers, actually, if we have labels here, if we knew what these images are, and we had a data set which was perfectly labeled, so every one of them is classified, given a category, and maybe some evaluation of that category, we can use something like Alexa. Basically, this becomes a classification task. This works only in a supervised scenario, which means that we have dataset with labels. And in that case, we basically don't need the decoder at all. We basically would train a classification network here and extract some intermediate layer here and say that this is our feature extraction, or this is our feature description that we want. Without those labels, what you might need to do is use some unsupervised methods, and these are the autoencoders and also GANs, as we will see later in the class, and use a network like this, throw away the decoder basically, and have a image to some intermediate representation as the feature extractor. Well, the intuition here is that if the encoder is good enough or creates a good enough representation that the decoder can sort of get back into the original version of the image, then this compressed information will be good enough for us in some other scenarios as well. So this is a sort of compressed representation of this image, but let's say that if this compression maintains enough information that it can be actually reconstructed well into the original image, we can say that this compressed representation can be used in other scenarios as well. So maybe we could plug this network as a face to something descriptor and then use that to control some interactive application. Okay, and let's see another sort of non-traditional use of an autoencoder, and that one would be this one, where we can train a autoencoder on some first dataset, on our kind of first dataset, have it sort of be able to reconstruct images from that dataset back into their original representation, and then come up with images from a second dataset, replace those here, have already trained a model from the first dataset, and sort of not try to retrain it, but basically just reuse it as a reinterpreter. So what will happen then is that these images from a second sort of domain are being compressed and decompressed using all the information that was in the first domain or in the first dataset. What may happen is that this reconstruction will not be really perfect. It will not be perfect. We will lose a lot of information from here because this model was never sort of supposed to actually encode these images, right? It was supposed to encode images from the first dataset. But as a consequence, what may happen is that these images will be sort of reinterpreted through the compression space of the first dataset. So we can sort of see this in the example of these two videos where the model has been trained on the Blade Runner movie. So the autoencoder is trained to sort of reconstruct images from the frame by frame sort of scenes from the film, and it's doing quite a good job actually. I mean, some scenes it's not managing quite well, but some are doing better, right? So you can still sort of see the shapes and recognize the scene, let's say. But if you then use it with some other dataset, like this one, then you can see that the other sort of material is being reinterpreted by the first network. So this is the Koyanikatse film by Sergei Reggio, with amazing music by Philip Glass, where the imagery from that movie is being reinterpreted through that model that has been trained on the previous sort of dataset. And so what you can see is that it's quite good at some maybe close-up scenes, because in the movie there are a lot of close-up scenes, so it's capable of finding shapes of humans, but it's maybe failing in the moments where we have some large non-detailed scenes, so some overview scenes where this reconstruction is basically a blob, which is without any sense. So there are other types of methods how to sort of transfer style from some dataset to another dataset. So this is not it perfectly, but it's sort of still maintaining some of that. We will talk about those models later as well, I think, maybe in the next class. Okay. Well, so if you want to know a little bit more, there is more written about this on a blog. Okay. So this was up until now explaining details about the autoencoder model. Let's have a pause now, and after that pause, let's talk about other types of generative models, particularly the generative adversarial networks. Okay, so let's go back to the beginning, where we had this sort of drawing of a generative model, where we have a latent vector, there is some magic here, and we generate an image, where we know that this magic probably will include some upscaling and convolutional layers, but still. And let's talk about the other type, or the second architecture, which we often use in generative models, and that is the Generative Adversarial Network. So with the previous model, we were sort of adding to the left of this sketch. In this case, we are sort of adding to this side. And in previous case, where this was a sort of identity operation, we are rephrasing this task as a two-player game. So one network, this one, is supposed to generate images, and then we have another one which is responsible for discriminating if these images are good enough or close enough to the real ones, basically. Well, this network is sort of responsible for telling if they are real or if they are generated. Well, we call these two networks one the generator and one the discriminator. Hence my mistake in some previous slides, where these two networks are sort of part of the same model, but we have a sort of smart training scheme which is used over the dataset. So let's see. So somewhere at the start, where none of these two networks are trained, basically what happens is that we have a vector which is random, and we generate some images from there, but because the network is not trained at all, the images we generate are rubbish. Basically, they are also like noise. So from random, we get random. The first step, sort of, is to train the discriminator. And so the discriminator sees two types of images. It sees images from the real dataset, and then it sees images which were generated by the generator. And its only task is to discriminate or to distinguish between these two categories. So learn that these are real and that these are fake. Basically, this is a classification task where we have two labels, real or fake, and we are assigning these to these images. Well, when we do that for a bit, we will freeze this discriminator, so not allow it to train. And notice that we have been using just this part of the network until now. And then we will start training the generator. And with the discriminator frozen, so it means that it's learning nothing new, we will try to teach the generator to make images which are which look less like the noise, but look more like anything that would fool the discriminator into assigning them with a real class. So we are trying to sort of motivate the generator so that it creates images which would fool the discriminator. And when we are doing this, we are sort of getting the error of the label all the way from here and propagating it through this discriminator network all the way to the generator network. However, this whole network is frozen, so we are only changing the weights of the generator network. Okay, and so at this moment, I think I would like to also say that this looks like a schematic right now, but inside these there are some upscaling and convolutional layers, and inside these there are some downsampling and convolutional layers. Basically, maybe some fully connected layers here, and maybe some fully connected layers here. Basically, it's a lot of it's reusing the same building blocks that we talked about in our previous classes, but just to make it simpler, these are shown as these sort of blocks rather than the whole amount of layers and everything. Okay. Well, so we talked about one iteration of the training where we were training the discriminator first to be able to distinguish between these two images, and then the generator in the second round where we are trying to make the generator better so that it can fool the discriminator. Well, this would not be enough. We are basically repeating this iteration again and again. So we are repeating this training process by switching between training the discriminator and then training the generator, while always freezing the other one which is not being trained. And so in doing this, they both get better at their task. One of the possible metaphors that we can use is that the generator network is sort of like a counterfeit artist, and its job is to mimic real artworks. It has never seen real artworks, but it's sort of trying to create some samples. The discriminator is an art curator who is sort of responsible for looking at real artworks and then some mimicked or some counterfeit art, and then being able to distinguish between these two. And so to spot the fake or the generated images. And basically it's an arms race between these two, between the counterfeit artist who is trying to make better artworks in every iteration, making better and better artworks, and his sort of only guidance is if the discriminator or the art curator will say yes or no. And it's an arms race between the counterfeit artist and the art curator who is responsible to distinguish between these two categories. And in doing so, they are both getting better at their job, sort of. So this is a visualization of training of some DC GAN, deep convolutional GAN, where it's relatively old model, but still, yeah. So what happens is that over the training, over the iterations of the generator and the discriminator, the generator is getting better and better at creating images. And so there are some smart ways how to sort of measure that, because you need to be training this in some way, and so there are different types of losses and everything, and we don't need to go into too much depth there. But what is important to see here is that where we started with some noise at start, and sort of something which is getting closer and closer to real images, we will end up with something which is actually quite realistic. And so the generator is getting better and better at mimicking real art or real data, let's say, without actually ever seeing, without ever having the access to this dataset. So we will sort of illustrate it here. So in here there is more detail about the training process. So we have named these parts of the GAN in a generator network, discriminator network, having some latent variables here, Z, similarly like in the AutoEncoder case. We can call the images that we create through generator, if we feed them with Z, as Y, and then images from the real dataset as X. So when the discriminator is being trained, it has these two types of inputs. And what we are doing here is basically just training it with the classification task to assign images from here with a label 1, and then assign images from here with a label 0. So in this training, we are sort of only using the discriminator and training the discriminator. The generator is basically just being used to, it has been used to generate a bunch of these samples. We can do this separately or we can do it on the fly. However, we are not changing anything in the discriminator. It's purely on the, in the generator, sorry. It's purely on the discriminator to sort of train in this stage. Okay, so in the, the data that we feed in as X and so as the data in and then the outputs out would be something like this, right? So everything from the dataset comes with label 1, everything from outside of the dataset, so everything generated would come from with the label 0. And so we saw something like this when we were talking about convolutional neural networks, where we also had a bunch of images and we are sort of assigning labels to them. And in that case, it was maybe 1000 labels or 10 labels in case of MNIST, but in this one, you only have real and fake. So we sort of have an intuition how this network could train, right? Because it's simply a classification task. We would even use the same types of errors here probably as we used in the previous cases. Okay, well, when training the generator, one thing which is important is that we phrase the discriminator, meaning that we don't change anything with it. We don't change anything with it. We just phrase it. And so we can say that we are sort of just using it to we are just using it during the process, but not changing anything in there. And we are training the generator G so that when we convert an image with it, when we get an image Y, which is something generated, we want the discriminator to mislabel this image as real. So you can see that in the previous stage, the discriminator was supposed to be labeling these with zeros, and now we are trying to change the generator in a way that it will fool this discriminator, so that these newly generated images, which are different than the ones that we had here, hopefully better, that they would be labeled with 1. So in this, you can see that the generator doesn't really have access to the real data, to X, because we are training it only from the errors propagated from the discriminator. So at some moment, you can say that when we are training the discriminator, it sort of learns the image representation of the X of the real dataset. It gets it inside its memory, and then the generator is sort of pulling those memories of that network or the representation that it trained into the generator network. And so it is eventually getting images which are the same as in the real dataset. However, it's sort of not doing it directly. And the reason there is that if it had access to the real dataset, it would start faking this task quite soon, because it would start just copying images from the real dataset. So what happens here is that we are sort of forcing it to figure out its own way how to generate images which are same as the ones in the real dataset. Okay? Well, so it's important to say that this training is actually quite fragile. So we need to balance training between the generator and the discriminator. And as such, there are a lot of techniques that are used to maybe balance these two networks, and also maybe figure out different ways of different losses that can be used, different training schemes, and there is a lot of literature there actually. So this is the basic version of the model. We will talk about some of the interesting uses as well. Okay, well, so we got here. We basically trained a GAN. Well, that's good. And we will now talk about the ways how we can sort of interact with this generative adversarial network. So similarly, like in the previous case with the autoencoder, we can sort of toss away some parts of the network. We basically can just throw away the whole discriminator part and the whole original dataset. We can only, or we can just work with the generator network on its own. We don't have to have access to the original dataset anymore. Okay? Well, so we can do almost the same as with the autoencoders before. So we generated some random vector here, and then we can feed this vector there and have a generator create images from that vector. And so this is trained on an anime dataset, and so it's creating images which are from anime or anime faces. So if we feed it with some random vector, we get one image, and then if we feed it with some other random vector, we will get another type of image. And so we can also sort of mix between those vectors to get interpolations there. So this is happening this is behaving the same as the autoencoder would, where we can interpolate between samples. Okay. So there is a block which talks about how GANs can be used in generating anime characters. It's actually quite surprisingly in-depth. They talk about the current state of the art, and they have some really smart ideas actually. So if you want, this is a good resource to read up about GANs in general, I think. Okay. Well, so what are the actual differences between GANs and autoencoders? Because we have seen that the interaction is sort of similar. Well, the main difference is that the autoencoders have the encoder part, while the GANs on their own in the default version, they don't have any encoder version. So they don't have a they don't have a network which would represent images from the real dataset into the latent vector representation. So we actually cannot encode real samples. So we have to depend on randomly generating images and then maybe assigning them with, okay, this one looks similar to the real sample that I saw somewhere in the dataset. So why would we even use GANs if they don't have this this kind of useful type of interaction? Well, if you look at the results of using an autoencoder and GANs, this is the original image, and this is how it is being encoded and then decoded. And then the same here. So these are pairs of encoded and decoded images. Let's say that these are the generated images. Then when you compare the results from the autoencoder and a GAN, you can see that the results from GAN are actually quite much better. They are much sharper. They have a lot of more details. And sort of intuition behind this is that in this moment, when training autoencoders, we had we were training it with a loss function, which is comparing these two images, and so it's comparing it pixel by pixel. And so the best approach to this is actually to strive from some average results, because those results, the average images, will actually have best errors in terms of a square distance. Well, what it does is that it sort of hides away the detail, the high dimensional features from there. It sort of leaves with the low frequency noise, or with the low frequency information, so the main shapes, but hides away the high frequency information, like the noise and the details. But in images, we actually have a lot of noise and details which are important, and so this is why the results from GANs are better. And the reason why GANs can include these details in a better way is that the error is propagated from, even for the generator, it's propagated from the discriminator. And the discriminator gets it from the real dataset. Well, so it's indirect way how to get the error metric, whereas here it was directly comparing pixel to pixel. And so this is, in the cases of GANs, it's basically a smart way how to train a network to fool it to actually maintain all of those details as well. Okay, well, so let's talk about some of the famous GAN architectures, because you might encounter it again and again, and it's also a good starting point if you want to sort of try something on your own with GANs. And one of them is the so-called progressively growing GAN. This GAN network, or GAN model, looks more or less the same as the previous sketches we had, and it's famous for being able to have very high resolution images as results. Basically, what we saw here, these results are from the progressively growing GAN. Well, what it does is that it trains this whole architecture while iteratively adding some layers into the generator and discriminator. So it's basically progressively increasing these resolutions of these two networks, of the generator and of the discriminator. And so it's adding layers by one by one layers of convolutions and upscaling to sort of start at the very coarse information and then add in details. And so this is actually really good model. In my own experience, it is the most stable one for even when we're working with your own custom datasets, which are maybe smaller than what they were training it on. This training scheme is actually quite smart in a way that it can. I was able to train a model which was working with like 3,600 images, whereas the original dataset was working with or the original model was working with something like 30,000 images, and in high resolution, so in 1,000 by 1,000 pixels. So I would suggest this model even for like small projects that you might have. And so this is the representation of that training process. we basically start with a generator and discriminator being very small. So it's generating some like 4x4 images basically at start, and then upscales it one by one. So 4x4, 8x8, all the way to 1024 by 1024. And so if you look at the results there, so it's able to generate images of this quality. And so you can see some amount of some sort of uncanny effect there. You can sort of notice some details are not making sense. Hey, what is this? Maybe, hey, the faces are not symmetrical in some cases, or maybe the background is broken. But overall, this is really high quality of what we are able to train. So there are some other datasets as well, which were lower resolution, and I don't know, they are able to sort of like generate horses, generate plants. Right, okay, so this is the visualization of the training process. So you can see the resolution at which the generated images are produced is increasing from, let's go back, from something like 4x4, slowly over time increasing the resolution into something more usable. And so I think this is what makes the network quite smart and powerful, is that it's sort of easing in the training process. And you can sort of also get the network which was somewhere at this moment, so you can get the version of the network which worked at this resolution and then use it for your own projects. Okay, well, so one thing that the progressive GAN was a little bit criticized from is that it focused on datasets which are very focused actually. So it was training on dataset of just faces. And so while it's able to sort of maintain really high resolution of images and actually quite high quality of generated images as a dataset, it's not able to sort of capture a dataset which would have a lot of images in there. So here comes the big GAN, which is a model trained by Google with their infinite clusters and infinite compute power. And basically they said that in order to do that, in order to train a model which would be able to capture large sort of diversity of images inside that dataset, you simply need to make a larger model and train it with a bigger batch size, which is something that needs tons of memory. So and trained it for a lot of time. So basically, this is a GAN which works with very diverse datasets. And so what it means is that you can have a dataset which includes images of dogs, of pets, and images of objects, and then you can explore the interpolation between those categories. So it has many categories inside the dataset rather than being simply focused on just one category. One caveat is that you cannot really train your own big GAN model because you simply wouldn't have the compute for that. While with the progressive GAN, you can do that even with like a medium / high-end GPU card, probably by NVIDIA, and it will probably take maybe weeks or something, but still it's feasible to do it on your own PC. But training something like big GAN on your own is not really possible. But what they did is that they released the big GAN models, and you can sort of try working with them and then try finding strange latent vectors inside that space as well. Well, so that gets us into the category of the weird uses of GANs. And the first one would be to searching through the latent space of existing pre-trained released models and then trying to find some maybe weird vectors or trying to find some things to do with those vectors. Okay, and so that would mean, for example, the work by Mario Klingerman, who is releasing a lot of his work on his Twitter. And so there is almost endless amount of sort of projects that he's creating all the time, and you can just go in the history of it and just see really weird stuff. But yeah, it's almost endless. But like I chose one sample, and that's where they used similar gun to the progressive gun, but the sort of next version of that gun, which is called style gun, which is even better at generating faces. And they mapped vectors which are describing music into a latent vector representation, and then used those vectors which are describing that music, and then use that description vector, the feature that was extracted from the music, let's say, to generate new images from the GANs. Or maybe they used some sort of, yeah, I don't know exactly the details of what they used. I think they might have maybe just mapped some categories between some samples that they previously found. Because at that moment it's a little bit difficult to work with GANs because you don't have the encoder segment of that network. However, they were able to do something like this. Okay, so basically, I think what they were doing were mapping beats to some movement in the latent space. So every beat would move the face in the direction of a, I guess, from a closed eye version of an image into a open eye version of an image. And so finding those categories inside the StyleGAN space was probably a bit difficult, but they were able to isolate some samples and then generate some vectors and create these visual attribute vectors, which would correspond to some behavior in the generated space as well. So there is, yeah, you can check other types of this sort of work. Yeah, another example is the project Art Breeder, or also known as Gun Breeder. And so it uses the fact that a gun such as the big gun contains a lot of imagery, and we can sort of almost endlessly search through it and find different shapes that are maybe of some weird interest for us. And so they released this model on a website and allowed people on the internet to go through these images and find the ones that they deem interesting, take them and maybe edit them by some small mutations and sort of explore where some crossovers between two images would go. And so this is a sort of approach from genetic algorithms, and with a collaborative sort of aspect to it. And so with the fact that we have somewhere the latent vector representation, which is sort of only 512 numbers, this is something which is relatively easy to save and also to just cross over between two samples. You can start with this and then add some small mutations, and then, or maybe add two vectors together and see where one interesting sample would get you with this human curation. So let's see an example here where let's say that this is the found sample in the dataset or in the generative network, and other people were sort of starting with the same point and then slowly editing it in a small ways, and those small edits, small mutations to the vector was generating these variations of that image. So at this moment, it doesn't have to be really figurative. You can sort of play around with abstract shapes, or you can get to sort of cross categories. I think this was maybe a flower or maybe a bird, and then it's going into a category of under the sea or more in the direction of flowers. So what they have is that I think only one of the models is the big gun. I think they trained also other types of models, and they have images of portraits, of landscapes, of art albums, or album covers albums. or again anime portraits, and it's actually quite cool, I think. So like you can start with some portraits and generate your own samples. Let's see. Okay, so I logged in, and this is this is how it looks when you have an account there. You can sort of start looking at other people's explorations of the space and see what they found in there, and maybe isolate it as samples that they wanted to maybe save. And you can see that this could be used as a source of inspiration for other projects, maybe, or maybe quite easy way how to generate some resources for your, let's see, everything is in there. You can generate some inspiration for later sort of pieces of art. So let's see if I think I found some. Right, so we can maybe, you can see that there are different types of imagery in there. So they're creating sort of album concept art or faces, or you could use this as a generator for a as a suggestion of faces for maybe a game or something like that. I think the only problem in there is that the resolution of this image is relatively low. Right, yeah, 512 by 5. Oh, yeah. Okay, so there is some amount of detail there, but you can see that it's quite pixelated. So at that moment, I think you could use something like super resolution GANs to again sort of upscale the resolution, and then actually use this as concept art in some game. You could have these characters as characters in a game. The really nice part of this whole project is that it's Creative Commons 0, CC 0. So it means that you can reuse anything that you create here for whatever you want with within any projects, commercial or not commercial. Okay, yeah, so we can mix this image with another one. And so this would be the same as you saw, let's say, content of this, so this face, but style of this, so this type, and you would get some images in between, or you can directly access some categories that they had to label. Okay, very focused. Yeah. Okay, so enough of this. This is interesting website. I think you could spend hours and hours of searching through this latent space there, but it also is an illustration of a use of these GANs, I think. Okay, so this is another sort of use of the or sort of relatively new research about GANs. Actually, the paper is from 2019, I think. It's trying to put some or get some capabilities of autoencoders into GAN models. So, for example, encoding real images into the latent space of the model, and then being able to work with those images in the same way as encode and decode or generate the image. So, for example, in the art breeder project, you can mix any images sort of as you want, but the problem is that you cannot really upload your own image and start with that as a starting point. You have to sort of find the one from the space, from the latent space of generated images, and then try changing that. So with this capability of being able to encode a real image, you would get a latent representation that would allow you to do some editation of that image, rather than having to sort of find samples randomly. Okay, well, so let's have a pause now with these two illustrations of the models, so the AutoEncoder and the Generative Adversarial Networks in mind, and then continue later. Okay, so we are near the end of the class now. Let's bring those concepts that we learned about generative models into a bigger picture. So there certainly is a kind of neural aesthetic when you train a generative on any types of data. But I sort of want to question the idea if just mimicking a dataset is an artistic act on its own. I think I see it rather as a tool one can use. So you use a camera to represent reality with I guess with digital cameras or with analog cameras. So there is a lot of technology in there, and the choice of the film you will use in the analog version, color or black and white, or the ways how you develop it if you are using some special techniques in the dark room, the way how you interact with the film material itself. Well, all of that is sort of on the technology side, but still photography is a real art domain. So also using a paintbrush in some way is a lot of technology, but then you are creating artworks with it. And so I think I would talk about the way how generative models can be used as a tool. I think it's Mario Klingerman who has been talking about sort of neurography as being able to draw with neural networks. If photography is drawing with light or photons, then neurography is drawing with neural networks. Well, if all of this is true, then I think we should sort of study the tool that we are using, explore its capabilities, and in particular explore the ways how we can sort of interact with it as an artist. So what are the dimensions that we can have any sort of control over it? Yeah. So I think some amount of curatorial input can be in these 4 domains. So whenever you make some distinction and create 4 domains of something, it's for sure this will not work for everything. I know this. This is not perfect differentiation. And also I will show some artworks of these types, but it's not including everything, of course. But it's an attempt to sort of divide the ways of interacting with generative models in some understandable ways. So one of those ways is the choice of the dataset, then the choice of the architecture, then the types of interaction with the latent space, and then finally some neural network hacking or editing the architectures themselves. Well, so the examples for the first type of interaction, I think 2 artists are quite well known about to work with this, and some works that I would like to mention are the works by Anna Ridler and Memo Akten. So Anna Ridler was working with datasets which, for example, she herself drew. So the fall of the House of Usher, you can actually watch it, is something that she trained on her own drawings in collaboration with a generative model. And so it is trained on large amount of data, but the data is sort of coming from her own artworks. So it's a combination of really like manual labor process of creating these drawings and then training a neural network on them. The same applies to this other project with the tulips, the mosaic virus, where she was, I think it's actually using the progressive growing gun, but on the data set that is sort of very painstakingly collected over a lot of months of collecting tulips and then making pictures of them and sort of sampling samples which would fit into the data set and throwing away the ones which wouldn't. So I think that's a good example of some artworks which are focusing on the dataset curation. Another type of the work is by MemoActen, where this is a model which we'll be actually talk about next class, I think. But it's reinterpreting images that you sort of would know with content from other domains. So it's sort of translating any junk that you have at your own person into images of plants. And there are different types of models that would do different things as well. So of course the technical consideration of choice of the architecture is actually also important. So as you saw in the easy example of choosing between AutoEncoders and GANs, you probably would choose a GAN for some cases, but you maybe would like to encode some real images. So there is some decision making there as well. And of course, in both of these cases, there are many versions of different implementations and tricks, and so which one you will use and which one you will disregard is a big choice as well. But maybe it's more on the technical side. So in the category of latent space exploration, interpolation, well, you saw a lot of this in the work by Mario Klingerman and also the Artbreeder, where you can sort of play around the latent space and find things inside it. This is another illustration of the same concept, where behind this is the idea that things that are similar things that are visually similar will be encoded by vectors that are near each other, and those vectors that are near each other will generate images that are similar again. So this is a short demo where it's a collaboration between two models. One is encoding a face and the second one is generating an image. And what happens is that each face will get its own sort of own types of imagery. So whereas the girl there had images of one type, this guy will have images which look like fields. And so you can sort of use this interactively and then explore of, okay, these are images that are generated when using this face. This is my face. Or you can sort of play around with. Right, I should not play the music here actually, because it will get flagged as reuse and copyright claim. But anyway, so you can sort of use this as an encoding of faces and then see that this face is creating. I think there is some wild working with his eyebrows. So this is spazzing out the input image, but the constructed image is also spazzing out as well. So, well, this is sort of playing around with the latent space. So that would be the third type of interaction. And the fourth type of interaction in the classification that I arbitrarily sort of chose is that you can treat these generative models and sort of look at the different building blocks that they were used to create this. So this is a generative network where we have a latent vector here and generating an image here, but you can sort of look inside this illustration and then see that it's built from some upscaling and some convolutional layers, and you can actually then take that the weights from that convolutional layer, the tensor there, and then maybe start reconnecting, rewiring it, editing it somehow, adding some effects there, maybe treating it as a signal that you process through some DSP processes or something. You can basically play around with this as well, and it's sort of a different way of interaction than with playing around with the vectors or with training, because you're sort of misusing something that has been trained on one representation and breaking its representation away, sort of. And maybe it will, yeah, basically just neural network hacking or neural network bending. Yeah. So we will. This is near the end of the class, so let's talk a little bit about the practicum that expects you. We will talk about some demos with variational autoencoders. I would like to also talk a little bit about scraping the internet, so how you can sort of collect your own datasets and then plug it in your own models. And as you can see, maybe the results will not be as precise as stuff that we saw previously. over this class, but it's still like a intro demo into that. If any bit from this presentation sort of interested you in some way, there are more readings, additional readings that you can look at. So more in-depth details about variation autoencoders, well, autoencoders all the way to variation autoencoders, and what are the small differences there, and what is the logic behind the probability series with variational autoencoders. You can see how people are sort of visualizing the latent space, or you can look at the anime GANs, which are explained here as well. Okay, so in the follow-up classes, we will have more generative models. I'm not sure how much I will be able to fit in there. I would like to focus on these two sort of domains. So one is the style transfer or pix-to-pix models, which is sort of domain-to-domain transfer. And the other type of models I would like to also talk about is the sequential modeling. So modeling something which comes with as a sequence. So that could be spoken language, this could be music, this could be other types of events which come in sort of sequences. Okay, so for today, this is it. I hope you liked the class, and see you at the practicum.